We can divide the study of processor design into four main phases. First of all, we'll have a look at combinatorial circuits, sometimes called combinational circuits. One or other of those names just has to be a spelling mistake, but no one knows which one because it happened a long time ago and because they're both quite good descriptions of how the circuits are constructed. More important than the spelling mistake is what they do. Combinatorial circuits are the result of an attempt to make electronic circuits that mimic Boolean algebra, in particular the behaviour of its operators and expressions. And that attempt was really quite successful. The circuits exhibit all the desired behaviour, but because they exist in the physical universe they have some other properties as well. For example, they take time to react when their inputs change. That's both good and bad. It means, for example, that computers will never be infinitely fast, which I guess most of us would consider to be a bad thing. But strangely, it can also be useful. A number of digital devices are designed as feedback circuits, and feedback circuits don't work reliably and predictably if data moves around the feedback path in zero time. The other major physical universe property of combinatorial circuits is that they use electrical power, so digital logic designers have to ensure that a power supply gets to every logic device in a circuit. The only upside to that particular property is that because all the devices in the circuit need power, we can design in the abstract without taking power requirements into account, on the understanding that someone will make the power connections, if or when the slightly abstract style of circuits that we design in this course are implemented in real hardware. The next most complex type of circuit is called the sequential circuit. Sequential circuits may, and usually do, have external inputs, like the combinatorial circuits, but they also have a feedback path, so that one or more of their outputs is sent around again and used as an input. Sequential devices are thus a function of current inputs and previous outputs. They allow us to design useful things like memory and state machines, which are sort of like simple programs implemented in hardware instead of software. Our third phase in the move towards designing a processor is the concept of a computer architecture. We'll have learnt about the internal operation of a number of standard building blocks in the first two phases, and in phase 3 we'll start finding out about how to put them together so that they interact in predictable and desirable ways without our having to consider how they behave internally. Many of these devices can act in different ways according to what control signals they're given. The control signals are themselves standard logic signals, so in phase 4 we'll learn about designing controllers that produce the control signals that make the architectures behave one way or another and step through a series of actions. We'll examine a couple of intermediate complexity systems that combine architectural building blocks and controllers to perform some useful function before putting the whole thing together in a computer processor with an architecture that's capable of executing a set of useful data manipulation tasks and a controller that's capable of reading machine code instructions and generating the appropriate control signals that make the architecture do the right thing in order to actually execute a computer program. And Boolean algebra underpins this whole system. Now I've got to say that learning how a processor's instruction set is implemented in a controller was one of the great leaps forward in my own understanding of how computers work. It allowed a whole lot of other computing concepts to make sense, and that's what we're trying to achieve in this part of the course. Sadly, there isn't time in this course to cover all four of these topics and actually design a computer processor from go to woe. However, in the second year course we'll have a look at techniques for putting the various building blocks together to form a data processing architecture and designing a controller that makes the data processing architecture do whatever's necessary to fulfill the requirements of a sequence of instructions. A computer program, in other words. So, to summarise, combinatorial circuits mimic electrically the mathematical behaviour of a Boolean expression. Formally, we can say that their output is a function of their inputs. Circuits of that sort can perform a variety of simple calculations, but there are some aspects of a processor that require something else. Not a lot, mind you. Combinatorial circuits do nearly everything we need. But sequential circuits pipe one or more of their outputs back to be used as inputs. So, strictly speaking, the formula that I wrote for the combinatorial circuit still applies. The output is still a function of the inputs, but now we distinguish between two types of input: externally supplied inputs, data if you like, and inputs that are fed back from the circuit's output. In the formal description, I've called those outputs that are fed back to be reused as inputs previous outputs. Why? Well, as we've already noted, circuits exist in the physical universe, so whatever calculation they perform takes some amount of time. The outputs don't settle down for a little while after the new inputs have been presented to the circuit. Thus, there's a delay between providing a new set of inputs and the resulting outputs becoming available. If we imagine now to be the moment when the circuit starts calculating a new output, the feedback data that it's getting as input must have been the result of a prior calculation. So, formally, we say that the sequential circuit produces a result that is a result of current external inputs and an output that was generated from previous inputs. So, for convenience, we've called that a previous output. Architectures need to be told how to behave, so electrical signals that are electrically identical to the data signals are used, and formally the behavior of this type of circuit depends on external data, previous output, that's data output, and here's the new component, control inputs. Controllers usually work through a series of steps, so they need to know what their own previous state was so that they can work out what to do now. They're controlling the behavior of an architecture, so in general they'll need to know something about its state, and they may also need to receive inputs from some external source. Now, it takes a little time to describe all four phases of this development, so in this course we'll have time to work on the first two only, combinatorial circuits and sequential circuits. We'll leave discussion of the architectures and controllers until our Stage 2 paper. The first step towards our ultimate goal is to learn about designing circuits based purely on Boolean expressions. If this were a maths course, we might spend a fair amount of time exploring Boolean algebra to discover its properties and peculiarities. But it isn't, and we won't. However, I will just take a moment to make one observation about the fact that Boolean algebra is a two-valued algebra. Many people say that computers only manipulate zeros and ones, so they can never make really intelligent decisions. The fact is correct, but that conclusion is doubtful in the extreme. As you're probably aware, letters and punctuation symbols can be represented as groups of zeros and ones in the ASCII code. It's obvious, therefore, that Shakespeare lacked any real intelligence, because everything he ever wrote can be reduced to zeros and ones. And on the same basis, Einstein was a complete idiot. Of course, you can represent music digitally too. Should we say that because Bach followed a rigid set of rules for manipulating symbols when he wrote music, which is true, that he was therefore unintelligent? It's a ridiculous idea. If you want to argue that computers can't make intelligent decisions, don't base your argument on the way the data is represented. Now, I'm not just riding a hobby horse here. We're working towards machines that can make astonishingly sophisticated decisions. But we start with pieces that make very unsophisticated decisions. And at this level, they do only manipulate zeros and ones. Ultimately, what's more important is how computers manipulate information. The underlying representation of that information is irrelevant. But for the moment, our focus is on the Boolean expressions and their implementation as digital logic. So let's turn our attention back to that. There is some creativity involved in taking more or less vague descriptions and formalizing them as Boolean expressions. But once you've done that, producing a corresponding digital logic circuit is just a straightforward series of steps. No further creative input is required. We start with a truth table in which we list all the combinations of inputs that the device will have to handle, and then the output that it should produce for each of those input combinations. Let's say that we start with one input called B that could be true or false. In Boolean algebra, as we know, there are only those two possibilities. However, let's add another input called A, and that's independent of B. So B could be true or false when A is false, and B could be true or false when A is true. So the truth table doubles in size when the second input is added. In fact, each new input doubles the size of a truth table because the new input could be false for all combinations of the existing inputs, and it could be true for all combinations of the existing inputs. So the number of input combinations in a truth table will generally be 4, 8, 16 and so on. When you're drawing up a truth table, it's easy to make a mistake and leave lines out if you don't have some system for listing all the input combinations. The easiest thing to do to ensure that you include them all is to alternate F and T in the rightmost column, alternate pairs of F's and T's in the column to its left, and then, if there are more columns, sets of 4 F's and 4 T's, and the next column over sets of 8 F's and 8 T's, and so on. Although you really don't want to draw up truth tables with more than 4 inputs if you can avoid it. And if you find that an assignment or an exam question in this course requires a truth table with more than 8 rows, it's probably worth looking at the question again to check that you've understood it correctly, or that there isn't some way of abbreviating the size of the truth table to handle large numbers of input combinations. When we've listed all the possible combinations of input values, it's time to add a column showing the output values to the table. That is, for each input combination we specify whether the output should be true or false. Once we've written out the truth table, we've defined the device's behavior under every possible circumstance. The next step is to write a Boolean expression to represent the information in the truth table. That expression simply specifies all the input combinations under which the device's output may be true. Each such input combination produces a term in the resulting expression, and since any one of the input combinations we've identified is enough on its own to make the output true, those terms are combined with OR operators. In this case, if A is false and B is false, or if A is true and B is false, or if A is true and B is true, then the output should be true. Having done that, we turn the Boolean expression into a circuit diagram. We show the inputs on wires to the left of the diagram and their inverses as well, since a Boolean circuit usually needs the inverses of at least some of its inputs, and since inside a digital circuit the inverses of signals are often available for free, if you like, as a byproduct of the way the circuit is constructed. The little triangles with circles on their outputs are inverters, remember? They tell us that the output will be high, meaning that the wire will be 5 volts above zero when A, for example, is false, whereas the wire directly connected to A will be high when A is true. Our next step is to draw a number of AND gates, one for each term in the Boolean expression, and a multiple input OR gate to combine all the terms in the expression together. And we'll add a number of blobs of solder to indicate which signals the AND gate will operate on. And of course, we'll label the output with the Boolean expression that the circuit generates. We'll go through this process again in later examples, so if you feel you've missed out on some of the details, don't worry too much. You should fill them in detail during the following slides. The circuit diagram can be drawn in terms of idealized gates. For example, you can't buy a 5-input AND gate, so if you were actually implementing a circuit that combined 5 Boolean inputs, you'd have to fabricate a 5-input AND gate out of something else, either by combining a couple of 3-input AND gates as shown here, or by connecting the 5 inputs to a 6-input AND gate and tying the unused input of the gate to a high voltage. Remember, 5 volts counts as a high voltage here. We're not talking about mains voltages. But in this course we're not particularly concerned about such mundane considerations. We could always convert our idealized gates if we wanted to, but that practical skill doesn't teach us a great deal about processor design, and it's not actually necessary when we're designing the insides of integrated circuits, which is how real processors are implemented. Inside a chip, we can make AND gates with any number of inputs, no matter how unlikely, so you could stick with idealized gates in this course. Now, our aim is to design some of the building blocks that go into computers. Unlike in algebra, a computer is not a mathematical fiction, it's a real piece of electronic hardware, and it has to be built out of real electronic components. So our very first task is to decide how to represent the Boolean values true and false in a physical system. In brief, we use one voltage to represent true and a different voltage to represent false. True is represented by a high voltage, 5 volts in mini computers, so it's not a high voltage in the sense that it'll leap out and zap you. It's called high only because false is represented by a 0 volt signal, and 5 volts is higher than 0. Now, 5 volts isn't the only voltage that's used to represent true. Low-power computers like laptops benefit from a reduced maximum voltage, so they're often designed to run on 3.3 volts, 2.8 volts, or even less. I tend to write HI for high and LO for low out of long habit, and because it makes some of the tables that we'll draw up a bit neater. Incidentally, the reason that we use two-valued Boolean logic as the basis of computing devices is that it's easier to build hardware to manipulate a two-valued system than, say, a 10-valued system, which would allow us to represent decimal numbers directly. We can certainly distinguish 10 different voltage levels without any problems. Audio processing systems that convert analog input into a digital representation of sound take the output from a microphone and measure its voltage on a much finer resolution than that. So it's not only feasible, but quite common. But think of the size of the tables. We can't call them truth tables anymore, because they wouldn't be dealing with just true and false anymore. Perhaps we can call them digital tables. Instead of truth tables for the AND and OR operations, we'd have to define multiplication and addition operations using much larger tables. Instead of a 4-line truth table to combine two variables, we'd have a 100-line digital table to define a multiplication or addition operation. And the hardware that implemented that operation would have to have 100 separate sub-circuits to cope with all the combinations. Well, we could get away with fewer than that if we designed the circuit intelligently, but certainly the circuits would be far more complicated. After deciding on a convention for representing true and false in electronic terms, we can start thinking about what the operations would be like. First of all, we need a piece of hardware that mimics, in the physical world, the behavior of the AND operator in the mathematical world. We're all familiar by now with the appearance of the standard 4-line truth table combining two Boolean variables. We can draw up a similar table for the voltages that a piece of hardware would have to respond to and produce if it were to mimic the behavior of the Boolean operation. The inputs would be a set of voltage combinations, following a similar pattern to the patterns of trues and falses, or zeros and ones as we have here, in the truth table on the left. And its output column would have a series of highs and lows that followed the pattern in the result column of the truth table. Since this is the voltage table for the hardware equivalent of an AND operator, there'd be a true in the last entry, where both inputs are high voltages or trues. And all the other outputs are low voltages representing false. Well, such devices have been produced. They're called gates, and they're commonly available for a few cents at electronics supply shops. When we design electronic circuits, we use a diagrammatic notation with special symbols for the more common types of component. An AND gate has this symbol. The lines on the left are inputs, and whatever signals are handled by the AND gate are fed into it through wires, lines on the diagram, connected to the input terminals of the gate. The output is the single wire on the right. An OR gate is a similar piece of hardware designed to mimic the behavior of a Boolean OR operator. It too has a voltage table in which high voltages replace trues and low voltages replace falses. It's just as close a transcription as the voltage table for the AND gate was, so I'll leave it to you to draw it up if you wish. The symbol for the OR gate is this. Again, the inputs are the lines on the left of the symbol, and the output is the line on the right. Information doesn't have to flow from left to right through the gate, but it's more common to draw the gates this way round so that it does. Now, you'll notice that there are two features of the OR and AND gates that distinguish them. At the input end, an AND gate has a straight line, but an OR gate has a concave line. At the output end, an AND gate has a semicircle, but an OR gate has a point made by the intersection of two curves. It's important that you get both of these features of the AND and OR gates right when you're drawing them, or your circuit diagrams will be ambiguous. Our final standard gate is the inverter. This is a device that, if given a low input signal, produces a high output signal, and if given a high input signal, produces a low output signal. That is, it behaves as the electrical analogue of the Boolean NOT operator. Here's the circuit diagram symbol. Again, I've drawn the circuit with the input on the left, there's only one input for an inverter, and the output on the right. Notice that, like the symbols for the other gates, the AND and OR gates, this symbol also has two parts, both of which have to be drawn. The triangle is really the electrical symbol for an amplifier. In fact, all of these gates, inverters, AND gates and OR gates, are technically amplifiers, and that's an important part of their function, since it ensures that the voltage levels, even after the signals have passed through lots of gates, are still 0 volts and 5 volts, and haven't degraded to some indeterminate intermediate voltage. But for the most part, we can ignore the amplification aspect of their function. What matters is the logic function that the gates perform, and the logic function of the inverter is indicated by that little circle. You'll find the little circle turning up attached to devices other than an amplifier. Wherever it appears, there's an inversion going on, but the circle never appears on its own. It's always an adjunct to some other device. When we're drawing the circuit diagrams for Boolean circuits, there are some drafting conventions that we'll use to make the diagrams easier to construct and easier to understand. Mind you, these conventions only work because of some other simplifying decisions about how to design a circuit diagram. The first is that we start with a truth table, and the second is that we don't bother to minimize the resulting Boolean expression. So, first of all, let's think about the decision to start by drawing out a truth table. It's possible to draw a circuit diagram for a device based solely on a natural language description of how it should function without going through the process of drawing a truth table or a Boolean expression at all. But there are two reasons not to do that. First of all, the resulting circuits tend to be complicated and difficult to decode, and secondly, whereas the truth table approach forces you to consider every possible combination of inputs, if you convert a natural language description directly into a circuit diagram, it's only too easy to design a circuit that doesn't handle some of the input combinations. So, having convinced ourselves that truth tables are a good thing, based on these arguments, we then discover that there's another, more subtle benefit. They're very easy to convert into an expression in a simple, standardized form called OR of ANDs form, or if you want to sound erudite, disjunctive normal form. That's an expression in which each term includes all the inputs, and all the terms are at the same level. That is, there are no sub-expressions in parentheses. Thus, all the terms can be combined with a single OR gate. To produce an expression in OR of ANDs form, you simply read down the output column of the truth table, and wherever you find a 1 or a true, if you've used F's and T's, you put a term into the expression. That term includes all of the inputs in that row of the truth table, and it shows whether they need to be true or false. In the raw, unminimized expression, as derived directly from a truth table, all the terms have the same number of inputs. So in the physical circuit, the same type of AND gate can be used for all the terms. We find that those expressions suit a very simple, standardized drafting convention. It's a bit different from many circuit layouts in which information travels horizontally all the way across the diagram from left to right. Instead, we'll bring in the inputs all the way down the left-hand side of the diagram, and functional components will be laid out to the right so that any of them can pick up any of the inputs. So we start by running wires carrying input signals down the left-hand side of the diagram. Then, because Boolean expressions often involve the inverses of inputs, we add an inverter to each input and treat the inverted inputs as inputs as well. That's to say, we draw extra wires down the left-hand side of the diagram carrying the inverted inputs. Now we can put our other gates anywhere to the right of this input bus and pick out any input or its inverses simply by drawing a horizontal wire across the diagram between the appropriate input and the gate that uses it. The top gate here picks up A and not B. The bottom gate picks up not A and B. However, there's now a problem that the wires cross other wires, and we want it to be clear when there's an actual electrical connection between the wires and where they cross each other on the diagram without making any electrical contact. So we add blobs at the contact points. It's convenient to think of those blobs as points where the wires are soldered together on the diagram, although they don't actually correspond to any real physical soldered connection in the circuit. This is, after all, a schematic diagram. The physical layout of chips will probably be quite different from the arrangement of gates that we draw. And since it's now clear where wires are connected together, the input wires for the gates might as well cross all of the inputs. Then the transcription of information from the Boolean expression to the circuit becomes really simple. It's mainly a case of ensuring that you put the blobs of solder in the right places. Of course, you have to get the right number of inputs and the right number of AND gates, but neither of those tasks is exactly challenging. And of course, if the original Boolean expression involved more than one term, there's going to be an OR gate, which appears on the far right of the diagram. If the device generates more than one output, it's clear that more circuitry could be added underneath the first lot to generate the other output or outputs. While we're talking about drawing circuit diagrams, there's a point about intersecting wires that I'd like to make. We use the convention that interconnections are indicated by what I call a blob of solder. Some other people use a converse approach. They indicate a lack of connection by drawing a little bridge where two wires don't connect electrically. Now that looks okay when there's just a single pair of non-connecting wires in a diagram. However, in general, where two lots of wires cross each other, there are usually a small number of connections and a large number of non-connections. So with this humpback bridge approach, you're more likely to see something like this. It's a whole lot easier to see what's going on when you use the blob of solder approach. First, because the number of pieces of information on the diagram is smaller. Secondly, because with the blob of solder approach, the visual information, the blobs of solder, correlates with interesting circuit information. There's a connection between these two wires, whereas with the humpback bridge approach, the diagram is full of strong visual stimuli, the bridges, that do a really good job of hiding the information that actually interests us, the sets of wires that a particular signal should follow. Weird. Since arithmetic devices are a hardware implementation of arithmetic operators, the numbers they operate on are called their operands. Earlier, I alluded to the fact that lots of arithmetic devices use what's called a bit slice approach. That is, they're divided into modules, each of which handles a single bit from each of the operands. One module will input the ones bit of the two operands and generate a result based on that. The next module will input the twos bit of the two operands, and so on. The bit slice module typically generates a single bit of the result. There may be a carry from one module to the next to deal with the situation when the result is more than one bit. A good example of this would be the adder circuit. This involves a number of identical modules, each of which accepts one bit of one operand, let's call it A, and one bit of another operand, B, and possibly also a single bit carry-in input, and generates an output which we call the sum, and possibly a single bit carry output. Now, there's a similar but simpler circuit that resembles this called a half adder that doesn't handle carry inputs and carry outputs. Although it's often taught in digital logic courses, it isn't a great deal of use for doing realistic arithmetic, so we've jumped straight to the full adder circuit that can actually do something useful. And just for the moment, we'll also jump over the step of designing the internal circuitry of the full adder and assume that it already exists. What will it look like from the outside? I don't mean is it black or green or does it have hairy legs, but what inputs does it need to have? What outputs will it produce? And importantly, how does it connect to the other modules of the arithmetic unit? We already know that our bit slice module will have to handle two single-bit inputs, call them A and B, and a carry-in input, and it will produce a single-bit output called sum and a carry-out output. If it were working on its own, just adding up single-bit numbers, then there wouldn't be any carry-in input, so we could connect that input to a 0. The electrical representation of a 0 is conveniently a 0-volt signal, so to use the appropriate jargon, we'd tie that input low. Next problem. How do we connect this module up to the other identical modules to make a complete implementation of an arithmetic addition operator? Well, first of all, A and B are now going to be multi-bit rather than single-bit numbers, and our module is only going to handle a single bit of each number. So let's clear those labels away from the input. Next, the module we've drawn here will end up handling the most significant bit of the numbers, so its carry-in input shouldn't be 0 volts. However, we will want a carry-in of 0 for the least significant module, so let's just put the 0-volt source to the side for one moment. Now we can add the other modules of the adder. The carry-out output of each module is connected to the carry-in input of the next most significant module, except that the module for the least significant bit, the one at the extreme right, has that 0-volt carry-in input that we put to one side. And the module for the most significant bit has a carry-out that doesn't go anywhere. We would often take that to another piece of circuitry that would handle overflows. Overflow might or might not be an error, depending on what the program that was using the arithmetic unit was doing, but that doesn't concern us here, so we'll just leave the output dangling. Now for the input numbers. We've drawn a device that's capable of handling 4-bit numbers, so A and B should have 4 bits each. Each of the modules handles 1 bit of A and 1 bit of B, and we can label the outputs S0 to S3. But why start at S0? Because the least significant bit of the output is the ones bit, and 1 is 2 to the power of 0, remembering of course that binary numbers are base 2. The next bit is the twos bit. 2 is 2 to the power of 1, so it gets labelled as S1. The 4's bit is labelled S2 because 4 is 2 to the power of 2. The 8's bit is labelled S3 because 8 is 2 to the power of 3, and so on. So now we've designed the complete adder. Confusingly, the circuit called a full adder is just one module in this device. I'm sorry about that, but the name full adder is universally used, so we're stuck with it, misleading though it may be. And incidentally, while I'm on the subject of words that you may find confusing, the word arithmetic, with the emphasis on the second syllable, is a noun. It's a name for a branch of mathematics, whereas the word arithmetic, with the emphasis on the third syllable, is an adjective that describes something. So we're building an arithmetic unit that will perform some arithmetic. Anyway, let's get back to the design. We've now got a reasonable idea of how the full adder circuit, remember that's the name for the single module, not the whole thing, should work. That is the more or less vague description that we talked about before. So we can now start deriving a truth table for the outputs of the circuit. We'll start by drawing up a truth table with the appropriate inputs A, B and C, which conveniently enough abbreviates to carry in, which conveniently enough abbreviates to C. This corresponding circuit diagram will therefore show the three inputs and their inverses down the left-hand side. There are two outputs, sum and carry out, each with its own column in the truth table, and its own output wire at the right-hand side of the circuit diagram. Now we start filling out the truth table by listing all possible combinations of A, B and C. Note the pattern of zeros and ones in the table. The rightmost column has alternating zeros and ones. The next column to the left has pairs of zeros alternating with pairs of ones. And the leftmost column has a set of 4 zeros followed by a set of 4 ones. Having done that, we can start filling in the output values. The first row of the sum output is the sum of 3 zeros, so it's 0. And the carry output is also 0. The second and third rows both have a sum of 1 and a carry output of 0. The fourth row has a sum of 0. Now, that might seem somewhat surprising. If someone asked you what the sum of 1 and 1 was, you probably wouldn't answer 0. But remember that this is a bit slice architecture. It handles one bit of each input and produces a single bit of the output. It's just the same when you're adding up a whole lot of multi-digit decimal numbers. You write the numbers down one above another so that the digits of the same significance are in the same column, and then you deal with one column at a time. If the column you're dealing with contains 2 5s, for example, then the digit in the output column is a 0. Of course, there's a carry digit that goes into the next column. But if we think of the word sum as a technical term that means an output digit with the same significance as the input digit in a particular column, then it makes sense to say that the sum is 0. Well, that's precisely the situation that we've got here. 2 ones are added together, and of course the result of that addition is 2, but if sum is the part of the result with the same significance as the 2 input ones, it's a 0. And of course the carry output is a 1. The next row is another simple case, with a single 1 input producing a sum output of 1 and a carry output of 0. Then there are another couple of 2 1 input cases, each with a sum of 0 and a carry output of 1. Finally, 3 ones are added together, producing a sum of 1 and a carry output of 1. So now we can start generating the circuit diagram. We'll design a subcircuit that produces the sum output first. We start by scanning down the sum output column until we find a 1. So that entry in the truth table is telling us that the sum output is a 1. Whenever the A, B and C inputs are respectively 0, 0 and 1. So we add an AND gate to the circuit that detects when A is false. An AND gate produces a true output when its input voltages are all high. So we draw in a blob of solder that connects one of its inputs to a wire that has a high voltage on it when A is 0. Similarly, its second input is connected to the not B signal, which has a high voltage on it when B is 0. The third input should be high when C is a 1, so that input is connected directly to C. So now that AND gate will produce a 1 output when A, B and C are 0, 0 and 1 respectively, because in that circumstance all of its inputs will be high voltages. So, having done that, we proceed down the sum column, acting similarly whenever we find a 1. As it turns out, there's a 1 output in the very next row, which corresponds to A, B and C values of 0, 1 and 0 respectively. So we add another AND gate that will have a true or 1 output when there's a high voltage on the not A wire, a high voltage on the B wire, and a high voltage on the not C wire. Then it's down to row 5, and an AND gate that detects when A is true, B is false, and C is false. Finally, the sum entry in the bottom row of the truth table generates an AND gate that will produce true output when A, B and C are all 1s. Now, stepping back from the detail a little bit, we remember that if any of these 4 input combinations occurs, the sum output should be true or 1. So we put in an OR gate into the circuit with its input connected up, so that if any of the AND gates produces a true output, the OR produces a true or 1 output. So now we can move on to the second output, carry out. Once again, we scan down the appropriate column in the truth table, looking for situations in which the output is a 1, and inserting an AND gate into the circuit diagram with the appropriate connections. The first one detects when A, B and C are 0, 1 and 1 respectively. Then there's one that detects when A is true, B is false and C is true. One that detects when A is true, B is true and C is false. And finally, one that detects when A, B and C are all true. Oh, but wait, we already have a gate in the circuit that performs that last function. In fact, the last AND gate that we included in the sum subcircuit is connected up in exactly that way. So we pinch its output and feed it into the OR gate that belongs to this subcircuit as well. There's nothing wrong with doing this. It doesn't overload the electronics, for example. Gates are usually designed so that their outputs can drive 10 standard inputs, which is plenty for most situations. If you ever needed to drive more inputs than that, you'd incorporate a buffer device in your circuit. But we're not really concerned in this course with that sort of real-world detail. We're more interested in the underlying principles. So that's the end of our full adder module. Observe how straightforward, mechanically even, the process of constructing the circuit diagram from the truth table was. As we've noted before, that comes from 2 things. First, don't complicate the situation by minimizing the Boolean expression. In fact, we didn't even write the Boolean expression down. And the circuit diagram, with the inputs and their inverses drawn vertically down the left-hand side of the diagram, and the AND gates in a column on the right, makes it really easy to connect up any number of AND gates to any combination of inputs.